Hey everybody, it's Mr. Brew from Infinity, the Math Institute, and I'm very excited we're here for our very first lesson. And when I said I'm going to start at the beginning, I'm really going to start at the beginning. Number one, what is math and why do we need it? Math is simply a way of counting or quantifying something. That's all it is. Thousands of years ago, we needed to count how many pigs we had on a farm, or how many people we had in our family, or how many people lived in the neighborhood. And we would just count 1, 2, 3, 4, and that's it. I mean, that's all we did. We got into other things such as 2 dimensions, like maybe not thousands of years ago, but right now we lay carpet. You can't get 10 feet of carpet. You have to get 10 feet by 5 feet of carpet. You need 2 dimensions. So we had to quantify in 2 dimensions. We also have volume in 3 dimensions. We're quantifying how much air is in the room, or we're quantifying how many particles are inside something, or liquid inside of a bottle. Either way, math is simply a way of counting or quantifying something. And we need it in order to communicate. How many water bottles do you see? Oh, I got 2 water bottles. I mean, that's how we communicate. We know what a water bottle is, and we know what the number 2 is. So they've been counting ever since the dawn of time. The first time we actually saw evidence of counting was in ancient Babylonia, or Mesopotamia, modern day Iraq and Iran, where they were able to write stuff on the walls of caves and stuff, and we noticed that they had counted stuff. What's amazing is they used a base 60 number system. Now what does that mean? It simply means they had 60 different symbols for the first 60 numbers. So you may realize we live in a base 10 number system. We simply have 10 symbols. Once we run out of symbols, we start a new column. It's really quite spectacular. Why did they use a base 60 number system way back when? Well, because they had very small numbers. The biggest numbers you would ever see is 120 or something. And the number 60 is divisible by 1, 2, 3, 4, 5, and 6, and 10, or whatever. But the bottom line is people had 1, 2, 3, 4, 5, or 6 people in their family. They had 4, 5, or 6, or up to 12 families in a tribe, or whatever you want to call it. So the base 60 number system worked really, really well when people were bringing goods and doing whatever they might be doing. How many pieces do you need? Oh, you need 5. Well, 5 times 12 is 60, or 6 times 10 is 60, or whatever the case may be. Obviously, this number system didn't work really well when we got into really, really, really big numbers. There were other number systems like the Roman numeral system. The Romans, they were absolutely amazing, amazing people and very innovative, but their number system was absolutely horrible. And then obviously we got into the base 10 number system, which is actually a form of, a Middle Eastern form number system. We use Arabic numerals as opposed to Roman numerals. And with our Arabic base 10 number system, it's actually beautiful. And it works so well that we've been using that number system for the past 2,000 years, or at least 1,500 years. And what's great is that you add another column, just multiplies it by 10. You take a column away, it's divisible by 10. And while it doesn't work for dividing as well as the base 60 number system, we have the advent of fractions and decimals. So we found a way to make it work. Is it perfect? No. We're going to get into all that later. The base 10 number system has a lot of flaws, and those flaws we call irrational numbers. Those decimal points that go on and on forever. But I don't want to get too far ahead of myself because we're going to save that for another lesson. Today, like I said, we're just going to start at the beginning. We're going to be talking about prime factorization. All numbers, especially whole numbers, are made up of prime numbers. They're a unique product of primes, and we're going to get into all this into detail today. But first, I want to review your homework. Those of you who saw my introductory video knew that I assigned a few things to you, because you're going to have to know your multiplication, you're going to have to know your addition, you're going to have to know your squares and cubes. Just remember, the only thing I'm ever going to ask you to do is add or multiply. And the only thing I'm going to ask you to do it to is numbers and variables. So if you can cook, if you can follow instructions, Follow my lead. We're going to take it step by step, and we're on our way to doing high-level math. Kids, adults, you're all welcome. I'm very excited. Let's get started. So, for homework, you were told that you have to memorize all of your multiplication facts from 1 through 12. You were also told to memorize the squares from 1 through 15 and memorize your cubes from 1 through 10. So here is your first quiz. Also, on that multiplication homework, I'll give you another copy of it on this. You'll always be able to find the links below, or I'm going to take some video of it. You could always pause it and print it, or pause it and write it down, whatever the case may be. But if you're able to print out the stuff, all the better. What I want you to do is take out a piece of paper and number it from 1 through 10. You can pause the video if you need more time to number your paper and just get ready. This is going to be your first example of our weekly squares and cubes quiz. This will be the easiest one. It will get much harder, and obviously I need you to get a perfect score on it. And until you get perfect scores consistently, I need you to practice it. Make index cards. I recommended buying index cards. I'm going to be giving you some vocabulary, and I would love it if you not only did your squares and cubes on index cards, but also did the vocabulary. It's amazing how important vocabulary is in mathematics, yet it's never stressed as much as it should be. Until now, of course, because here at Infinity, we stress index cards, we stress vocabulary, and while I'm going to be explaining all the concepts to you so you fully understand it, you are going to have to memorize some things. It's just the way it is. I'm so sorry. Okay, here's your first squares and cubes quiz. I will give you 5 seconds to answer each question, and after 10 questions, you're going to grade yourself on a scale of 1 to 10. You should be getting 10s. It will begin in 5 seconds. 3 squared, 5 cubed, 7 squared, 2 cubed, 11 squared, 1 cubed, 12 squared, 3 cubed, 8 squared, 4 cubed. Time is up. You should be done. Just to let you know what the answers are, they are 9, 125, 49, 8, 121, 1, 144, 27, 64, and 64. Hopefully you got a perfect 10 on that. If not, it was just the first time. I'm going to give you a pass, but I promise you, next week's quiz will be a lot harder. Memorize 1 through 15 and 1 through 10. Again, here are all the documents you're going to need. On the left here, you see your multiplication quiz. If you don't have a printer, you could just pause the video right now and take this quiz. It should take you less than 5 minutes to complete this 100-question quiz perfectly. This is also a copy of today's vocabulary. I'm going to be going over them word for word, but if you wanted to pause the video and write it down, so that way instead of writing while I explain, you could pay attention, that would be even better. This is going to be our first packet. This is our Introduction to Math packet. Again, you could pause it and write all this information down, or if you'd like, you could print it from the link provided below. This is pages 3 and 4 of that same packet. This will be your homework for next week. You can pause the video and write it down, or you can print it out using the link below. All right, so first things first, we're going to talk about our vocabulary for the lesson. I'm going to explain it to you the best I can as just giving you the vocabulary and the definition. But if you don't fully understand one of these vocabulary words, fear not, because we're going to be using all of them throughout today's lesson. So further explanation will be provided. But really quick, a prime number. It has 3 components. It's got to be a whole number, not a decimal or a fraction. It's got to be a whole number. It's got to be greater than 1. Therefore, 1 is not a prime number. A whole number greater than 1 whose only factors are 1 in itself. So obviously the first prime number isn't 1 because it's not greater than 1. The first prime number is 2. 2 times 1 is 2, and that's the only way you could do it. 3. 3 times 1 is 3, only way. 4. That is not only 1 times 4, but you could also do 2 times 2. Therefore, it's a composite number. A composite number technically is a whole number greater than 1 who has factors other than 1 in itself. But a little shorthand way of saying it is not prime, you know what I mean? Every number, every whole number greater than 1 is either prime or composite. 2 is prime, 3 is prime, 4 is composite, 5 is prime, 6 is composite, 7 is prime. 8 is composite because you have factors of 1, 2, 4, and 8, not just 1 and 8. An integer, just because I'm going to be using that, we're going to go into a whole lesson about integers all by itself, and we're going to talk about the classifications of numbers. But it's good to know just right now that an integer is whole numbers and their opposites. So that opposites refers to negatives. So while whole numbers are 0, 1, 2, 3, 4, and all the numbers you might find on a number line, no fractions, no decimals, integers are the whole numbers and the negatives. So all the negative numbers up to 0, and then 1, 2, 3, and up to infinity. All whole numbers and their opposite. An exponent, which you may or may not know, is a superscript. A subscript is an annotation down and to the right of a letter. A superscript is an annotation above and to the right of a letter or number. This annotation to the top right of a number denotes how many times you multiply a number by itself. So 2 to the second power is 2 times 2. 2 to the third power is 2 times 2 times 2. 2 to the fourth power, 2 times 2 times 2 times 2. Very, very good. I'll get into this more later, but subtraction is simply adding the opposite. 8 minus 4 is the same thing as 8 plus negative 4. I don't expect you to change your way of thinking. 8 minus 4 is 4 no matter how you slice it. 10 minus 2 is 8. All right, but just for the algebraic sense later on, it's good to understand that subtraction is just adding the opposite. 10 minus 2 is 8. 10 plus negative 2 is 8. Division. It's just a form of multiplication. It's multiplying by the reciprocal. So, when you have 8 divided by 2, which is 4, obviously, it's the same thing as 8 times 1/2. 8 divided by 2, 8 times 1/2. Multiply by the reciprocal. Now, the reciprocal, you can think flip, but don't say that in front of me. The definition of reciprocal is two numbers whose product is 1. So the reciprocal of 2, 2 over 1, is 1 over 2. Yes, you flip it. That's your shortcut. But the truth is 2 times 1/2 is 1. 2/3. The reciprocal of 2/3 is 3/2. But 2/3 times 3/2 is 6 over 6, which equals 1. So the proper definition is two numbers whose product is 1, but you could think I'm just going to flip it. The fundamental theorem of arithmetic. Now this is the most important one, and we're going to go over this in depth, all right? But do you even know what fundamental means? Fundamental means essential, super important. Theorem, this should be an index card in a vocabulary word. Theorem is something that's been proven. Once something's been proven, once something is a theorem, it cannot be unproven, and you don't have to prove it again. Once you prove something, that's that. So, something essential that's been proven about arithmetic. What is arithmetic? It's just mathematics and the basic mathematical operations. So the fundamental theorem of arithmetic is something super important and foundational that has been proven about math. Yet, nobody really knows what it is. It's amazing. This is the one thing you should have taken away from elementary and middle school. The fundamental theorem of arithmetic states every whole number greater than 1, the same prerequisite says prime numbers, is a unique product of primes. Unique, one of a kind, product, multiply, primes. Prime number is a whole number greater than 1 whose only factors are 1 in itself. We're going to get into how to do the prime factorization or utilize the fundamental theorem of arithmetic in today's lesson. We're also going to be talking about the GCF. You should know that stands for the greatest common factor. And the definition is the greatest common factor is the largest number that divides into two given numbers. I'll show you an example in just 1 second. LCM, the least common multiple, is the smallest number that two numbers divide into. Very important that you're able to say it that way so that way you don't get confused. We spoke about the base 10 number system. It's simply a number system that uses 10 different symbols. Once we run out of symbols, we start a new column. We're going to get into that in detail as well, everything. But some other number systems that I didn't mention. Binary. Every time you see a movie that has to do with computers, you just see the zeros and ones fill up the screen. Well, that's because there's only 2 symbols. And once they run out of symbols, they start another column. And everything in computers goes back to the binary system. Simply a yes or a no, or a 1 or a 0, or a black or a white. It's the most primitive form of counting there is, and it's very effective. It's what's making you able to watch this video right now. Relatively prime. That doesn't necessarily have to do with prime numbers per se. It just means that there's 2 numbers with no common factors. Yes, 2 prime numbers are also relatively prime, but you could have composite numbers that are relatively prime. Like the numbers 4 and 9. They have no common factors. The only factors of 4 are 1, 4, and 2. The factors of 9 are 1, 9, and 3. 1 doesn't count because it's not a prime number, so they have no common factors, or the only common factor is 1, however you want to look at it. And you need to memorize the first 10 primes. You really should be able to recognize almost any of the primes, especially in the single and double digits. And there's a great game going around on Facebook right now, Is It Prime? Turned on to me by Jan Awasi, a former principal in Hawaii, and she's always got the greatest math games. Thank you, Jan. Anyway, so the first 10 primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. You need to be able to recite that on any time that I ask you. And remember, 9 is not prime, it's 3 times 3. 15 is 3 times 5. 21 is 3 times 7. And 27 is 3 times 9, or better yet, 3 cubed. Nonetheless, get comfortable with all these words. We're going to be using them quite a bit. And again, vocabulary is essential. So let's get into the lesson. All right, so the first thing I want to talk about is I wanted you to be able to visualize what the GCF and the LCM actually are. So say we have 2 numbers like 15 and 20, right? You have to be able to understand that the GCF is the biggest number that divides into both numbers, which means you should be able to visualize that 5 is the GCF. And then, can anybody tell me what the LCM is? All right, the LCM is the smallest number that the given 2 numbers can divide into. All right, and that would be 60. All right, now, there's a couple of ways that we could do this. All right, the most basic way, which is not the way I'm going to want you to do it, but I am going to want you to be able to visualize this. All right, the factors of 15 are 1, 3, 5, and 15. The factors of 20 are 1, 2, 4, 5, 10, and 20. All right, so you should be able to see that the biggest number that divides into both of these numbers, or the biggest number or factor they have in common, is 5. And that's it. That's the greatest common factor. Obviously, it's not going to be that easy when we're talking about much bigger numbers or more complex situations, but you need to be able to visualize that. At the same time, what are the multiples of 15? The multiples of 15 are 15, 30, 45, 60, 75. The factors of the multiples of 20 are 20, 40, 60, 80, 100. All right, so which number do they have in common? What's the smallest number that they are both contain that multiple? 60. All right, so you'll be able to find the least common multiple and the greatest common factor by writing these things out. But obviously, we're here to give you some shortcuts. Now, in elementary school, you may remember factoring numbers. All right, and I'm guessing you used a factor tree, which is the messiest, least effective, and economics of time is the fastest and is not the fastest or most efficient way. But let's take a look at an example. What is the prime factorization of 30? All right, well, we made our factor tree, right? 30 is equal to 2 times 15, and that's not the only right answer, but 2 is prime, so we could stop. 15 is 3 times 5. These are both prime, so we could stop. Meaning 30 is equal to 2 times 3 times 5. Just for all of you wondering, we will be using dots as multiplication signs. We will not be using an X because we're adults now, or young adults, whether you're in 6th grade or you're 60 years old. We'll be using dots instead of an X because we're going to use X as a variable, right? All right, so the prime factorization of 30 is 2 times 3 times 5. Let's do another quick example. Let's say we have the number 40. Why don't you pause it really quick and make sure you could do this on your own. And now we'll check your answer. 40 is equal to 4 times 10, both of which are composite. 4 is 2 times 2, both of which are prime. And 10 is 2 times 5. So the prime factorization of 40 is equal to 2 times 2 times 2 times 5. Obviously, there's an easier way to do this, which is why I introduced exponents to you earlier. This is actually equal to 2 cubed times 5. The prime factorization of 40, 2 cubed times 5. One last example. We have the number 100. All right, and again, there's no right way to get to the answer. There's a bunch of different paths we can take. Pause it, see if you could do this on your own, and now I'll give you the answer. 100 is 10 times 10. Both composite, so 110 is 2 times 5. And 10 is 2 times 5. Therefore, 100 is 2 times 2 times 5 times 5. Notice I always like to put the numbers in consecutive order. So I have my 2's first and then my 5's. And now you should be able to recognize also that we're not going to say 2 times 2 times 5 times 5. We're simply going to say 2 squared times 5 squared. And that's how you should be writing out your numbers. Now, obviously, I'm going to show you a much easier and more efficient way than doing this, much neater and more organized, with more redeeming qualities. Wait, it's going to get really exciting. But first, let's talk about the long way, the elementary way, the basic way of doing, say, the GCF. The GCF of 15 and 20, we already did, right? Let's do the GCF of 18 and 24. Well, like I said, the first thing you're going to have to do is you're going to have to write out the factors of 18. The factors of 18 are 1 and 18, 2 and 9, 3 and 6. The factors of 24 are 1 and 24, 2 and 12, 3 and 8, 4 and 6. What is the biggest number these have in common? It looks to me like it's a 6. So 6 is the GCF. Again, we could find the LCM of these two numbers. You would have to write out all the multiples. 18, 36, 54, 72, 90. I hope that's enough. Let's see. We have 24, 48, 72, 96, and 120. Lucky for us, it was enough in this instance. We have the number 72 appearing on both lists, and that's the smallest time it happens. So the GCF would be 6, the LCM would be 72. Again, I'm going to show you a shortcut, but in order for you to truly understand what's going on here, I'd like you to just practice these methods. So that way when we do the shortcut, you can actually see what we're doing. All right, let's do it again with the numbers 8 and 10. All right, pause it, make sure you can tell me the GCF and the LCM, and then hit play to make sure we got the same answers. Factors of 8, 1, 2, 4, and 8. Factors of 10, 1, 2, 5, 10. What is the GCF? It's 2. Now let's do the LCM. The multiples of 8 are 8, 16, 24, 32, 40. In fact, the multiples of 10 are 10, 20, 30, 40, 50. So there we go. We see that the least common multiple is 40. Again, I'm going to show you some shortcuts, but bear with me. Now let's take one final example. Let's take the numbers 17 and 20. All right? Number one, they have no common factors. What does that mean? Very good. They're relatively prime. The factors of 17 are 1 and 17 because 17 is a prime number. 20 is composite, but 17 is not a factor of 20. Only 1, 2, 4, 5, 10, and 20 are. So they have no common factors besides 1, so they are relatively prime. Now, I could write down all the multiples of 17 and all the multiples of 20. But let me just tell you something. If they have no common factors, if they're relatively prime, the bottom line is the product of 17 and 20 will be the least common multiple. 17 times 10 is 170, so 17 times 20 is 340. That would be the least common multiple. All right, so talking about least common multiple and greatest common factor, why is it so important? All right, we're going to be getting into all sorts of lessons involving fractions, decimals, algebra, equations, and we're going to see that if you have this mastered, you're going to cruise through the successive lessons that I teach. For example, if you had 1 over 8 plus 1 over 10, all right, we're going to need to know the LCM of 8 and 10 in order to add these fractions. If you don't understand what I'm doing right now, don't worry. We're going to be getting into fractions really soon. But I just want to showcase that the LCM is 40. Therefore, I know I have to multiply this by 1 in the form of 5 over 5, and this in the form of 1 by 4 over 4, which gives me 5 plus 4 over 40 is 9 over 40. All right, that's just a little spoiler for what's coming up soon, but this is why the LCM is so important. And there's an infinite number of other examples. But nonetheless, also, if we have 8 over 10, and I want you to simplify that, well, we need to divide by the GCF of both numbers. The GCF of 8 and 10 is 2. So we divide by 2, and we end up with 4/5. That's why knowing the greatest common factor is important. There's going to be other examples. You could have like 10x plus 50, and we know the greatest common factor of both of these is 10. So I could pull a 10 out and call it x plus 10. X plus 5, I'm sorry. Nonetheless, I'm just showing you some examples here and there of how we're going to be utilizing these skills and why mastering them will make your future lessons all the easier. But let's get into the easiest way to do this. First of all, let's do the prime factorization of, say, 18. All right, I take the number 18 and I build a little house around it. All right, we've been calling this the Mr. Brew method over here at Infinity, but the truth is I stole it from one of my great professors over at UNLV, and you know, it's Dr. Shu's method. That's how I learned it. But I learned it from Dr. Shu, so I call it Dr. Shu's method. You're learning it from Mr. Brew, so I don't think Dr. Shu will be that offended if you called it the Mr. Brew method. Either way, we're all good. So once we have built a house, what we're going to do is we're going to take the first prime number. What's the first prime number? Correct, 2. Does 2 divide 18? It does. How many times? 9. Does 2 divide 9? No, it doesn't. So what's my next prime number? 3. Does 3 divide 9? It sure does. How many times? 3 times. Does 3 divide 3? It sure does. 3, 1. Once I get to that 1, I could stop. What is the prime factorization of 18? It's 2 times 2 times 3. Which also is 2 squared times 3. Now notice, not only is this neater, but it gets us the answer in order, so we don't have to redo it. We don't have a factor tree all over the board or all over your paper, so you're able to organize your thoughts a lot better. And there's more redeeming qualities to this method, but we're not going to get there yet. Give me a couple of minutes. I want to give you a practice problem. Let's do the prime factorization of 25. You can pause the video and try it yourself, or you should be able to just see it on your own, right? 25. 2 does not divide 25. 3 does not divide 25. The next prime number is not 4, but 5. Does 5 divide 25? It does. 5. How many times? 5. 5 divides 5 one time. So 25 is equal to 5 squared. Which you all knew because I made you memorize the squares and cubes. Nonetheless, here it is showcased. The prime factorization of 25 is 5 squared. That's a unique prime factorization, meaning 25 only factors down to 5 squared, and 5 squared only equals 125. So it's a unique product of primes. Last practice problem. Let's do the prime factorization of the number 150. All right, now that you've unpaused the video because you tried this alone at home, let's do it together. The lowest prime is 2. 2 does divide 150 75 times. 2 does not divide 75. Does 3? In our next episode, we're going to talk about divisibility rules, but a little preview. 7 plus 5 is 12, and 12 is divisible by 3. Therefore, 75 is divisible by 3. How many times? 25. And spoiler alert, we already know that the prime factorization of 25 is 5 times 5, right? So 150 is simply 2 times 3 times 5 squared. 2 times 3 is 6. 5 squared is 25. 6 times 25 is 150. That is the prime factorization of 150. All right, let's talk about how we could take this to the next level. Now, when we're doing the GCF and the LCM, we could do the same thing, but simultaneously. Check it out. If we have the numbers 25 and 50, and we wanted to find the GCF, all right, build your house. Does 2 divide both of these numbers? No. It divides 50, but it doesn't divide 25. Does 3? 3 doesn't divide either of them. 5 plus 0 is 5. 2 plus 5 is 7. Neither of those numbers are divisible by 3. 5 is the next prime, and how do we know if something's divisible by 5? If it ends in a 0 or a 5, which both of these do. So 5 is a common factor. It goes into 25 5 times, and 5 goes into 50 10 times. Guess what? 5 divides both of these numbers as well. It divides this 1 time, and it divides this 2 times. I can stop when these two numbers are relatively prime, when they no longer have any common factors. And now what do I have? Oh my gosh, right here is the GCF. The GCF of 25 and 50 is equal to 5 squared, which is 25. All right? You may not have needed to use this method, but later on, when the numbers get more difficult, this is a great tool to have in your toolbox. But wait, there's more. Look at this. It also gives me the LCM. The GCF is the column that we factored. The LCM is the bottom and the left side of the column. So the LCM is equal to 5 times 5 times 1 times 2. which is 50. The least common multiple of 25 and 50 is 50. All the answers are right here, and look at how nice and neat it is. Organized, and you've got your thoughts together. So, I want you to try one. Let's do 30. Oh, no, let's do 18 and 60. Let's do 18 and 60. Tell me what the GCF and the LCM of 18 and 60 are. And then after you do it, unpause me and I'll show you how good you have done. I'm very impressed, by the way. Yes, 2 divides both of these 9 times and 30 times. 2 does not divide 9. 3 is my next prime. 3 does divide both of these numbers. So it's going to be 3 and 10. And 3 and 10, while they're not prime, both prime, they are relatively prime, so I can stop. The GCF is simply 2 times 3. Which is 6. And the LCM is equal to 2 times 3 times 3 times 10. 2 times 3 is 6, times 3 is 18, 18 times 10 is 180. And that is the LCM. Very good. Let's just do one more problem to make sure you guys are experts. Let's do, how about, this is a tricky one. All right, here's a couple of tricky ones. I'll do 2 of them. We'll do 12 and 14, which is not very tricky. And over here, we could do 32 and 81. All right, I hope you noticed a couple of things. The first thing you should have noticed is that these 2 numbers, they're relatively prime. 32 is equal to 2 to the 2, 4, 8, 16, 32, 5th power. And 81 is equal to 3 times 3 is 9, times 3 is 27, times 3 is 81. So the prime factorization of 32 is 2 to the 5th. The prime factorization of 81 is 3 to the 4th. Therefore, the only factors of 32 are multiples of 2. The only factors of 81 are multiples of 3, relatively prime. So the GCF is 1, or there is no GCF, however you want to look at it. And the LCM of 32 and 18 is 32 times 18. How does somebody like me, that people think I'm a human calculator? I'm not. How do I do 32 times 18? Well, 32 times 10 is 320. 32 times 20 is 640. 32 times 2 is 64. So I do 640 minus 64, which is 600 minus 24, which is 576. So the GCF is 1, the LCM is 576. Do you have to be able to do that multiplication in your head? No, you don't have to. You could write it out. But I'm just telling you, I'm not a human calculator. I just organize my thoughts in my head. 32 times 10 is 320. 32 times 20 is 640. So 32 times 18 is 576. 12 and 14, that was a fun one. You should have noticed that it's simply 2. 6 and 7 are relatively prime. So the GCF is 2. The LCM is 2 times 6 times 7. 12 times 7 is 84. That's one of the numbers you had to have memorized, right? 2 is the GCF, and 84 is the LCM. Very good. Do a couple of more practice problems. What I want you to try is we're going to do the prime factorization of 50. 175 and 2142. All right, pause it, try to do those 3 problems, and I'm going to come back and do them really, really quick. I hope I don't go too fast. I tried to go really slow earlier. I'm going to go a lot faster right now. You should have gotten 2, 25, 5, 5, 5, 1. So the prime factorization of 50 is equal to 2 times 5 squared. 175 is not divisible by 2. 1 plus 7 is 8, plus 5 is 13, which is not divisible by 3, so it's not divisible by 3. So I'm going to go with the number 5, because it ends in a 0 or 5. 5 goes into 175 35 times. 5 goes into 35 7 times, and 7 is a prime number. So 5 times 5 times 7. 175 equals 5 squared times 7. Finally, 2142. Oh my God, what a big number. Mr. Brew, why are you so mean? Too bad, deal with it. All right, so 2 does divide 2142. How many times? 1, 0, 7, 1. Very good. 2 does not divide 1071, but 1 plus 7 is 8, plus 1 is 9. 9 is divisible by 3, therefore 1071 is divisible by 3. How many times? 3, 5, 7. 357. Now, 3 plus 5 is 8, plus 7 is 15. Divisible by 3, 357 is divisible by 3. 3, 1, 1, 9. 1 plus 9 is 11, not divisible by 3. So what is it divisible by? Well, it's not divisible by 5. The next prime is 7. Is it divisible by 7? Well, 70 plus 49 is 119. So it is. 7 into 11 is 1. 49 is 7. And we know 17 is a prime number. Yes, this is the hardest one I gave you. But with a little bit of practice, it should be no problem. And your homework's going to have plenty of practice, don't worry. So 2142 is equal to 2 times 3 squared times 7 times 17. Want me to tilt it down a little bit for you? There you go. 2 times 3 squared times 7 times 17. Now, let's get into a couple of practice problems with GCF and LCM before I let you go. Last problems of the day. Find the GCF and LCM of the following 3 sets of numbers. 36 and 42. Let's do 30 and 50. And let's do 112 and 144. All right, tell me the GCF and LCM of these 3 pairs of numbers. All right, welcome back. All right, the first things first, we're going to make our house. It's going to be 2, 18, 21. 2 does not divide this, 3 does. 3, 6, and 7. 6 and 7 are relatively prime. So the GCF is equal to 2 times 3, which is 6. The LCM is 2 times 3 times 6 times 7, which is equal to 6 times 42. 10 times 42 is 420. 5 times 42 is 210. 6 times 42 is 210 plus another 42, which is 252. Not a human calculator. Just to organize my thoughts in my head. 30 and 50. They're both divisible by 2. 15 and 25. Not divisible by 3. Divisible by 5. 3 and 5. 3 and 5 are both prime, so they're relatively prime, so we could stop. The GCF is 2 times 5, which is 10. And the LCM is 2 times 5 times 3 times 5, which is 10 times 15 is 150. I hope you're getting all these right. I hope you could see my sloppy handwriting too. Finally, the last one, 112 and 144. 2, 56, 72, 2, 28, 36, 2, 14, 18, 2, 7, 9, relatively prime, I can stop. The GCF is equal to 2 times 2 times 2 times 2, which is 16. 2 to the 4th power, 16. The LCM is equal to 16 times 63. Do you want me to do that in my head? All right, 16 times 63. All right, I'm going to write this down so you can see what I see in my head. I don't know if you really want to get inside my head, but I'm going to bring you inside my head really quick. All right, when I'm doing 16 times 63, all right, the first thing I do is I say 16 times 10. I'm sorry, 63 times 10 is 630. 63 times 5 is half of 630, is 315. And we need 16 of them. Here's 10 of them, 5 of them. 63 times 1 is 63. So I can do this in my head too. 630 plus 315 is 945. 945 plus 63 is 8. I'm sorry, I'm trying to explain and do it in my head. I'm screwing up, but my apologies. Either way, it's 8, 10, and then 10. I hope that's right. 63 times 16. Now I have to double check my answer because my brain is all over the place. But let's do it the old-fashioned way. And parents, teach your kids the old-fashioned. You don't have to teach them the Common Core way with the arrays and the boxes and everything. Teach them how to multiply. The bottom line is kids know how to need to have these skills. All right? If they understand how to multiply, then that'll make it the weird Common Core way that much easier to understand and digest. But I digress. 63 times 16 is 18, 36, 37, 63 is 8, 0, 1. All right, I got it right. But yes, I promise you, Mr. Brew makes mistakes just like you guys do too. All right, I assigned 4 pages of homework. For example, on your first page here. All right, I want you to fill out all the vocabulary words and answer these questions regarding our discussion as we began. All right, then the next 3 pages are problems. All right, the next 2 pages are all prime factorization and GCF and LCM problems. And the last page is just a way for you to organize your thoughts, all right, to understand that 9 squared is 81, all right? Write down all your squares and cubes. You should have your squares up to 15 and your cubes up to 10, but nonetheless. And then on these problems on the bottom, I just want you to exercise your understanding of addition and division, subtraction and division. 10 minus 2 is equal to 10 plus negative 2. 12 minus 6 is equal to 12 plus negative 6, which equals 6. 100 divided by 20 is equal to 100 times 1 over 20, which is equal to 5. I just want you to get into the habit of recognizing subtraction is adding the opposite, division is multiplying by the reciprocal. Like always, I went way over time, but I just love teaching you guys. We're going to get into some really crazy stuff, and it just starts at the beginning. 1 step at a time. Come back next week knowing your squares, your cubes, your prime factorization, fundamental theorem of arithmetic, your GCF, your LCM, and be ready for a quiz on not only your squares and cubes, but we're also going to have an index card quiz where I'm going to be asking you about your vocabulary. You should be able to know it just like that. All right, guys, it's been a lot of fun. I could do this all day, and I'm going to be doing it forever. All right, we're starting right at the beginning, and I'm going to take you all the way through to calculus. It might take a couple of years, but we're going to keep it fun. We're going to keep it light. We're going to keep it simple. Practice this a little bit every day. I would appreciate it if you did 10 minutes of homework every day instead of an hour worth of homework in one night. That way you're practicing. Just like if I told you how to shoot a free throw, it's going to be better if you practice that form 10 minutes a day than just 60 minutes on a Sunday. So do a little bit of this every day. Don't overwhelm yourself. Memorize your facts. And I can't wait to see you next time here at Infinity, the Math Institute. If you have any questions or you need anything, email me, tutor at themathinstitute.com. Visit our website, themathinstitute.com, or check out our Facebook or our Instagram or our YouTube. Obviously, you must have checked one of them out if you're watching this video. Thanks again. Don't get more math problems, get solutions.